Hi everyone, this is my video number 27. So I'll talk on the alternative method for converting inertial value problem into Volterra integral equation. And alternative method for converting inertial value problem into Volterra integral equation. So what we'll do in this video that first, how do we convert the inertial value problem into Volterra integral equation? So the step is exactly as we done in the previous lecture. And the next is how do we convert from the obtained Volterra integral equation back to the original inertial value problem. Yeah. So that's the purpose what we are going to do. So I will begin with example, and basically I will give you a few examples to describe how do we do the conversion. Yeah. So let's consider first example is that first we just convert the inertial value problem into integral equation. Yeah, convert the inertial value problem into integral equation. Right, it's not well focused. All right. The given inertial value problem is that y double prime x plus lambda yx is equal to fx, y0 equal to 1, and y prime 0 is equal to 0. Y prime 0 is 0. Okay, now first thing, we write the given inertial value problem, the given equation, into y double prime as a main subject. Yeah. Solution. We write, let's call this equation 1. So write 1 as follows. So we have y double prime x. This is equal to fx minus lambda yx. We normally y, okay, doesn't matter, y or u doesn't matter. So in this case I use y. Okay, so if we integrate this equation here, those one, and then let's call this a boundary condition, so easy for us to call, so let's call this equation number 2. Let's give a name, this is equation number 3. Okay, now then we integrate the equation 3. Yeah, integrate 3 from 0 to x, from 0 to x. Alright, with respect to x, so what we got is that integrate those, we got y prime x, then we evaluate from 0 to x, and then we integrate everything there, then integrate those 0 to x, we have fx minus lambda yx dx. Alright, and then of course you can evaluate those that give us, if we evaluate this, we have y prime x and y prime 0. Y prime 0, we can use the boundary condition 2 here. Alright, so what we got, simplify those, simplify, and using the boundary condition, the initial condition, the initial condition 2, which is we use y prime 0 is equal to 0. So what we have, because y prime 0 is 0, so that's 0. What left is that we have y prime x. This is equal to integrate from 0 to x. We have fx minus lambda yx dx. Alright, so let's call this equation 1, 2, 3. Let's call this equation number 4. And then we integrate again. Integrate 4 from 0 to x dx. So what we have is that yx, y prime, we integrate those, we got yx, then integrate from 0 to x. That gives us, we integrate this again, we have 0 to x, fx minus lambda yx dx twice. Alright, I've explained in the previous video what we mean by that. So this and then you can of course simplify this, and then you can use the boundary condition, and then simplify, and using the initial condition 2, in this case we have y naught is equal to 1. Alright, so here what we have is that yx minus y naught is 1, and those 1 we bring it to the right side. So what we have is that yx is equal to 1 plus 1 plus integrate 0 to x fx minus lambda yx dx squared. And then we use using integrate from a to x y yt dtn. This is equal to integrate from a to x, okay, x minus t n minus 1 over n minus 1 factorial y t dt. So using that, we can write this as a, of course from there you can change a variable yt to have this. Alright, so we got this thing. You can change it to t, just the variable of integration, and then we can apply those. So if you do this, we going to have yx is equal to 1 plus integrate 0 to x. So we have x minus t, and then this is n is 1, so n is 2. Alright, so that we have 1 factorial, and then those things we have fx, we change that to ft, so ft minus lambda yt dt. Okay, so this is the integral equation that we're looking for. We convert from the given initial value problem, the equation number 1, then we obtain those equations. So let's call this 1, 2, 3, 4. Let's call this equation number 5. So this is the required, this is the required Volterra integral equation of the second kind. Alright, so I'll give you another example. One more example. So next example is that how do we do both, converting from the initial value problem into the Volterra integral equation, then we convert back into the from the obtained Volterra integral equation, we convert again to the given initial value problem. Okay. So example, let's say we have a given y double prime x minus sine x y prime x plus ex yx equal to x. Alright, with the initial condition y 0 equal to 1 and y prime 0 equal to minus 1. So let's call this equation number 1. Let's call this equation number 2. If you still got confused with this, you can refer to my previous video. It's not really difficult to do it, just the step might be a little bit longer. Alright, so we can write those given differential equation, yeah, right, one as we have y, we bring the others to the right side, and then on the left just y double prime. So we have y double prime x, this is equal to, we have x minus ex yx plus sine x y prime x. Okay, so let's call this equation number 3, and then we integrate 3 from 0 to x with respect to x. So that gives us that one we integrate, we got y prime. Alright, and then those y prime we evaluate from 0 to x, so then y prime 0 is negative 1. Alright, so I just put in everything together and using 2. Alright, so we're going to have a y prime x, this is equal to, we integrate those, we have x squared over 2, and then we have minus 1, you got minus 1 plus, alright, we have sine x yx, for this is come from here, where to obtain that we use the integration by parts. Alright, so you have this term, one term, and the other term that's involved, we integrate differentiate those things. Alright, so that give you minus integrate from 0 to x. Alright, we combine with that, so we have ex plus cos x yx dx. So let's call this equation number 4. Now we integrate again 4 from 0 to x dx, and again using the initial condition given in 3, using 2, we have yx is equal to s cubed over 6 minus x plus 1 plus integrate 0 to x sine x yx dx, okay, minus integrate from 0 to x ex plus cos x yx dx squared, yx dx squared. Okay, then we change the variable of integration from x to t. So what we have, or you can write this, yx is equal to x cubed over 6 minus x plus 1 plus integrate 0 to x. Alright, this is our function in front here, 1 plus 1. Is that okay? Yep. So we have integrate 0 to x, so sine t yt dt, alright, and minus integrate from 0 to x. So here we have x minus t. In this case, we have used the relation that we have integrate. We have 0 to x yt dtn. This is equal to integrate 0 to x minus t n minus 1 over n minus 1 factorial, okay, yt dt, dt. Oh, yeah, this relation here. So we end up with that, and then minus, so we have x minus t et plus cos t yt dt. So let's call this equation 1, 2, 3. This is equation number 5. And of course here you can rewrite this or simplify that, make it the integral, put it under one integral signs. So we have this give you yx is equal to x cubed over 6 minus x plus 1 plus we integrate from 0 to x, then we have sine t minus x minus t et plus cos t yt dt, So this is the required Volterra integral equation, because you can see this is our kernel kxt, all right, and this is our known function fx. So that gives us the Volterra integral equation of the second kind. Alright, now having done those, we are going to convert the given the obtained Volterra integral equation into the given initial value problem. Yeah, so that's the second step. Now, so let me write those. Now we convert the obtain Volterra integral equation into initial value problem. Okay, so to do that, we differentiate 5 with respect to x. So d dx 5 with respect to x. So what we have is that y prime, so 5 is here, that one, so just differentiate those with respect to x. Alright, so we have x squared, 2x squared, then cancel out, we have x squared over 2, yes, 3, minus 1. Alright, so we have this, give you x squared over 2 minus 1, alright, plus d dx integrate from 0 to x sine x minus t et plus cos t, is that this one? Okay, that bracket, and yt dt. Remember that in doing this we need Leibniz rule. Okay, we need Leibniz rule in order to evaluate this. I think I have explained this in my previous 2 videos, if I'm not mistaken, 2 or 3 videos. Yeah, so we use the Leibniz rule. So what is the Leibniz rule? Is that we integrate everything inside with respect to x, and then we evaluate at the upper limit minus evaluate at the lower limits. Yeah, so let's do those things. So using Leibniz rule, so we have y prime x, this is equal to x squared over 2 minus 1 plus we integrate from 0 to x, differentiate everything inside that with respect to x, so we have del x sine x minus x minus t et plus cos t yt dt, and then we evaluate everything with respect to we evaluate those at the upper limit. So we have plus we have sine x minus, then here x minus t, so x minus x, so we have x minus x, and then here e to x cos x, so we have e to x plus cos x, and then yx. Alright, and then we have yx, and then dx. We differentiate the upper limit, and then do the same for the lower limit, minus we have sine should be sine x minus x minus 0. Alright, minus x minus 0, then we have e to x x minus t sine x minus t e to 0. Okay, so e to 0 minus cos 0, and then y0, and then we differentiate the lower limit. So d0 dx. Alright, so simplify this and don't forget to differentiate those with respect to x. Then we will have y prime x. This is equal to x squared over 2 minus 1 minus integrate from 0 to x. Differentiate inside with respect to x, so we have et plus cos t yt dt, and then the rest, this part is 0, right? This part is 0. Alright, what left is only that. Then this part is also 0 due to that. That one is 0. So what left is sin x yx dx dx is 1. So that give you plus sin x yx. Yeah, sin x is from here, sin x yx. So sin x yx. So let's call this equation number 6. Now we have from a differential equation of second order, now we have reduced one order into just one order 1, y prime. Then we integrate again. We differentiate again, we differentiate again. From y, you got y prime, and then we differentiate this. Now differentiate with respect to x, d dx 6. Okay, so what we got, y prime, that give you y double prime x plus this is equal to, this one is differentiate, we got those two cancel out, we have x, and then plus differentiate those, we got cos x yx, cos x yx, and then differentiate respect to y, so we have plus sin x y prime x, and then inside the integral sign we have negative d dx, we integrate 0 to x e t plus cos t yt dt, yt dt. And again we use the Leibniz rule. Using the Leibniz rule, we have y prime, y double prime x is equal to x plus cos x yx plus sin x y prime x, sin x y prime x. Alright, so this part we use the Leibniz rule, that gives us minus integrate 0 to x del x et plus cos t yt dt, alright, plus e to x plus cos x, we evaluate this at the upper limit, dx dx, dx dx, minus at the lower limit, so we have e to 0 plus cos 0, y0 d0 dx. Alright, and then simplify that, we have, okay, simplify those things, that give us, put it here. So simplify that, we got so we have y double prime, okay, so then that's give us y double prime x this is equal to x plus cos x yx, all right, plus sin x y prime x, and then inside the square bracket you got minus ex plus cos x yx, yx. So that's what we got. Or you can rewrite this, you bring it everything that involves y and y prime to the left and the function on the right side. So what we got, this is y double prime x minus that one sin x y prime x, okay. Then you got minus cos here, that's cancelled out, so what left is only ex. So we have plus ex yx, that's equal to x. So this is the original given differential equation. Now to get the initial condition, okay, so we just substitute x equal to 0 into we have y prime and y. So where is our y? Y is, no, just a minute, okay, y is equation number 5. So substitute into that, give you initial condition for y, and then we substitute into y prime. Y prime is 6, so 5 and 6, that give you condition number 2. So by substituting those x equal to 0 into 5 and 6, what we got is y 0 equal to 1 and y prime 0 equal to minus 1. So this is actually the given differential equation. Alright, so let me just give a briefly next example, another example, but I won't explain those in detail. I just give the main part only. Alright, so convert y prime x minus 3 y prime x plus 2yx equal to 4 sin x. 4 sin x with initial condition y 0 equal to 1 and y prime 0 equal to 2 into Volterra integral equation of the second kind. Alright, and again, having done those, we derive the original differential equation from the obtained integral equation, and then derive the obtained Volterra integral equation into the given initial value problem. Alright, solution. So as I mentioned earlier, that I'm not going to discuss this example in detail, so I just give the important parts only. Alright, so the given equation here, you bring everything to the right So we have y double prime x, this is equal to 4 sine x minus 2 yx plus 3 y prime x. Okay, so let's call this equation number 1. I just put it there. This equation number 2, this equation number 3. Alright, and then you can integrate this, and then using the given initial condition, that will give you y prime x. Okay, just right here, integrate 3 from 0 to x dx, and using boundary initial condition 2 give us that y prime x equal to minus 1 minus 4 cos x plus 3y x minus 2 integrate 0 to x y x dx. Alright, let's call this equation number 4. Then we integrate again, integrate 4 0 to x dx, and then again using condition 2, and then we end up with the required Volterra integral equation. Yeah, so we got yx is equal to 1 minus x minus 4 sine x plus integrate 0 to x 3 minus 2x minus t yt dt. Alright, so this is the required Volterra integral equation. Now from the obtained Volterra integral equation, we convert into the given initial value problem. So what we need to do there is just differentiate this, and then we need to use the Leibniz rule, and then again differentiate for the second time, again use the Leibniz rule, and then use the initial value to find the condition for the initial value. Right? Then so we differentiate 5. This is let's call this equation number 5. Alright, now we differentiate 5 with respect to x, so d dx 5, and then we use, and using Leibniz rule, that give us, I just jump everything, then we got, after simplify, we got yx this equal to minus 1 minus 4 cos x plus 3yx minus 2 integrate 0 to x yt dt. Okay, so let's call this 6. We differentiate again, yeah, d dx 6, again using Leibniz rule. Okay, so just don't write those things. So we end up with the y double prime x minus 3y prime x plus 2y x. This is equal to 4 sine x. So this is the given differential equation. Now for the initial condition, yeah, for the initial condition, for the initial condition, we substitute x equal to 0 into y and y prime, into yx and y prime x, which is equation equation number 6 and 5, yeah, which is equation number 5 and 6. You substitute into those, then we have that give you y0 equal to 1 and y prime 0 equal to minus 2. Okay, so I think that's enough for today's video. Let me let me give you some exercise for you, just one exercise for you. If you're given y double prime x minus 2x y prime x plus 3yx this is equal to 4 sine x. Just make sure they're different. Yeah. And then with initial condition, we have y0 equal to 1 and y prime 0 equal to 0. Okay, convert this into Volterra integral equation. Yeah, convert this into Volterra integral equation. Then again into the initial value problem. Alright, so that will be the end of this video. Now let me recap what I've done in this video. That given the differential equation of the second order, basically you can also work for the n order, because at the beginning of last video, I think I've given the general case, I mean to the n order of differential equation, and then we convert those given differential equation into Volterra integral equation. What you need to do is just integrate once and integrate twice, and then use a certain formula that also I have given to you, and then we obtain the Volterra integral equation. Now, from the obtained Volterra integral equation, in order to get back to the given initial condition, what we need to do is that we differentiate once and differentiate twice. So in this differentiation process, we need to use the Leibniz rule. Alright, then you can find what is y, what is y prime, and then what is y double prime. And then final part is that to find the initial condition, we just substitute the given initial value to find the condition into respective equation, y, or in our case of y and y prime. Alright, so with that we stop here for this video. Thank you for your times. Bye bye, see you in the next video.